Hi everyone, I am Maheshwaran. I am from EC, Assistant Professor. So today we are going to discuss on unit number 5, multiple antenna techniques. So in that we are going to discuss about MIMO systems and channel model development. So MIMO systems are multiple antenna technology which is devised for wireless communication in which multiple antennas are used for a single user at transmitter as well as receiver for the purpose of increasing the channel capacity as well as data rate. So the antennas at each end of communication circuit are combined to minimize errors and to optimize data speed. Multiple antenna setup is used to increase the channel capacity. So before we devise the channel model for any MIMO system or multiple antenna system, we need to understand or to get insights about channel capacity theorem proposed by Shannon. So Shannon's channel capacity theorem states that for a errorless transmission, data transmission for a given bandwidth, W in the presence of a noisy channel, it is given by C is equal to W log of 1 plus SNR, where W corresponds to the bandwidth which is measured in hertz, SNR is a dimensionless quantity, and C is the data rate which is measured in bits per second. So from this equation, the channel capacity is directly proportional to bandwidth W and directly proportional to SNR. So these are the four basic structures of spatial diversity systems using multiple antennas. First one is single input and single output systems in which we have only one transmitter and one receiver. So it is one-to-one correspondence. And the second case is it is MISO in which we have number of transmitting antennas which is more than one, and we have only one receiving antenna. It is NT:1 correspondence. The third type is single input and multiple output SIMO model in which it is 1:NR correspondence, which means it has only one transmit antenna and NR receive antennas. And the fourth case is multiple input and multiple output systems in which we have more than one antenna at transmitter as well as receiver. So the correspondence is NT:NR. So let us discuss the channel capacity for various spatial diversity multiple antenna systems. In case of SISO, the channel capacity is W log base 2 1 plus SNR, where NT and NR are assumed to be 1, as we discussed earlier. In case of SIMO, the channel capacity C is equal to W log 1 plus NR into SNR, where we have only one transmitting antenna and NR receiving antenna. So the factor is 1 here. So if you consider this as a general case, if you substitute NT is equal to 1, you can get SIMO model. And the third case is MISO, for which the channel capacity is depending upon number of transmitting antennas alone, not the receiving antenna. So SIMO model we can also call it as receiver diversity, and MISO model we can call it as transmit diversity. So in MIMO model, where number of transmitting antenna and the number of receiving antenna is greater than 1, so the channel capacity is determined by number of transmitting antenna as well as number of receiving antenna. So we included the factors NT and NR in the channel capacity calculations. So these are the different analytical expression which we use to calculate the capacity of various spatial diversity systems. So let us discuss the advantages of having multiple antenna systems. So the advantages of multiple antenna systems are: it increases the channel capacity, it improves the spectral efficiency, it improves the coverage area in case of wireless communication and mobile communication systems, improved user portion estimation in case of location identification navigation systems, improved data rate and low power consumption. So because here instead of having one antenna, we have more than one number of antenna, so the total power to be used is divided among n number of antenna, so it results in low power consumption also. So implementation of MIMO or multiple antenna techniques. In case of multiple antenna techniques, it can be implemented either as a diversity system or as a multiplexing system in spatial domain. So first we discuss about diversity multiplexing system. In case of spatial multiplexing, the definition is given that spatial multiplexing is a technique that uses multiple antenna systems to reuse the spatial domain for same signal in order to improve the data rate. So in case of spatial multiplexing, it improves the channel rate, channel capacity at a higher SNR, and it is used to increase the data rate. So if you consider spatial multiplexing, it takes the original data stream and it divides the data stream into two parallel streams, and both antennas are used to transmit different parallel streams. So the spatial domain is reused several times here. Here it is 2 times it is reused, and at the receiving antenna, the different versions of signals are combined and the original signal is brought back. So it is explained here. So spatial multiplexing is a transmission technique in MIMO wireless communication to transmit the original high data stream into several parallel streams. Each parallel stream of data is sent from one transmit antenna, therefore the space dimension is reused multiple times, more than one number of times. At the channel, these data streams are mixed up so that at the receiver antenna, the elements are supposed to be combined to brought back the original signal. So for that we use a appropriate signal processing or a decoding technique to carry out that process at receiver. So let us discuss in detail about the difference between diversity and spatial multiplexing. In case of diversity, we are transmitting the same data through different antennas. So here a data stream 101 is taken and the same data is being transmitted by different antennas. So this is diversity. And if it is in the case of spatial multiplexing, the high bit data stream is divided into high bit rate parallel streams. So here we have a bit stream supposed to be 101, and that bit stream is divided into 3 streams, 3 parallel streams, and each stream is transmitted by a different antenna. So if the same data stream is transmitted by different antenna, it is known to be diversity, and the data stream is divided into parallel streams and each parallel stream is transmitted by different antenna, it is known to be spatial multiplexing. So this is the very important difference between spatial diversity and spatial multiplexing. So we can use multiple antenna techniques to exhibit or to exploit both diversity as well as multiplexing, depending upon the application. So when you are using multiple antenna techniques for diversity techniques, so we will be calculating diversity gain, and in that case multiplexing gain is assumed to be 0, and while executing spatial multiplexing through multiple antennas, the multiplexing gain is to be considered and the diversity gain is assumed to be 0. So in this case we have 3 antennas transmitting the same data stream, so the diversity gain is 3:1, which is 3. So to calculate diversity gain we have a formula NT cross NR, where NT is number of transmitting antennas and NR is number of receiver antennas. Here we assume that there are 3 transmitting antennas and 1 receiving antenna. So on the other hand, if you are considering the spatial multiplexing, the multiplexing gain is to be considered and diversity gain is assumed to be 0. So to calculate multiplexing gain, we need to take the minimum of number of transmitting antennas and number of receiving antennas. Here in the case, the minimum of transmitting and receiving antennas, if we assume there are 3 transmitting antennas and 1 receiving antenna, the multiplexing gain is 1, because minimum of 3, 1 is 1. So this is how we need to calculate spatial multiplexing gain as well as spatial diversity gain. So this slide could reiterate the difference between diversity techniques and multiplexing techniques through multiple antenna technique. Now we are going to consider the MIMO system. We are going to devise the MIMO system model. So in multiple input, multiple output system, as discussed earlier, there will be more than one number of transmitting antenna and one number of receiving antenna. So here we have NT numbers of transmitting antenna and NR numbers of receiving antenna. Each antenna can have 1TN correspondence, which means transmitting antenna 1 can transmit to receiving antenna 1 to up to NR. Similarly, transmitting antenna 2 can transmit to receiving antenna 1 to etc. up to NR. So likewise, we have 1TN correspondence between transmitter and receiver. So the objective of the channel model formulation is to develop a mathematical model for wireless channel in matrix form for a MIMO wireless delay dispersive communication system. The channel model matrix H should contain the complex Gaussian random variables as its elements that models the fading gain between each combination of transmitting and receiving antenna. So let us assume that there are NT transmitting antennas and NR receiving antennas in our MIMO system. So for the model development, we need to consider several assumptions at the transmitting side. So at the transmitter, the data stream is encoded and is forwarded to NT transmit antennas. So from this antenna, the signals are sent to the wireless propagation channel, which is assumed to be quasi-static and frequency flat. Quasi-static means the coherence time is very large, so that the data rate can be improved. And the assumption of frequency flat is the channel parameters are not drastically changing for different frequencies. So it is almost same for all frequencies, the channel characteristics. So if we having these two assumptions, we can proceed to develop the model for MIMO channel. So even at the receiver, the data stream is received by NR number of receive antennas. From these antennas, the signals are combined or selected by an appropriate coding technique, and the original user data stream is reconstructed. So here, as discussed earlier, so here we are going to establish diversity technique. So user data stream is made available at different transmitting antennas. So the transmitting signal vector is formed by S1, S2 up to SNT, or you can have T1, T2 up to TNT. So likewise at the receiving side, the receive vector is assumed to be Y1, Y2 up to YNR, or R1, R2 up to RNR. So now our objective is to find out the matrix between this S2 and Y2. So how this S1 signal is transformed to Y1 signal, or how this transmitted vector is transformed at receive vector. That is our ultimate aim. So for that we are going to devise this channel matrix H. So the channel transfer function of, see, and in the figure, if you look, there are the matrix coefficient H11, H21 like this. So H11 corresponds to the signal from transmitting antenna 1 to receiving antenna 1. So the signal H, the matrix coefficient H21 corresponds to the signal received at transmitting and receiving antenna 2 from 1. So for example, if you have a coefficient H32, it means the signal from transmitting antenna 2 received at 3. So that way we need to take. So the channel so that was mentioned in this slide. The channel transfer function H21 represents that the data traveling from the first transmitting antenna to the second receiving antenna. So there are different combinations of channel coefficient. So received signal 1 can be assumed as the linear summation of H11 T1, H21 T2, H31 T3 up to HNT1 TNT. Similarly, received signal 2, 3 and received signal from receiver antenna NR are found out. So this linear combination of equations can be represented as a matrix of dimension NT cross NR. So if the linear equations are mapped into a matrix rotation, the received signal vector R vector is equal to the product of H vector into T vector. So thus the received signal vector Y can be obtained from R vector, and similarly the received signal vector S can be obtained from T vector. So by transforming this, instead of R vector we can use instead of R matrix we can use the vector Y. Instead of T matrix we can use the vector S, and the H matrix can be found by taking the inverse. So how will you find the inverse? How will you find the H matrix? R into T inverse, right? So and to be noted that there is an additional parameter which is N added to the equation. What is it N? N corresponds to the additive wise Gaussian noise, because we know very well that in a delay dispersive environment like a wireless channel, noise is inevitable. So that for our assumption, the standard white Gaussian noise is considered. So N corresponds to the additive white Gaussian noise that is involved with the communication process. So thus the matrix H11, H12 up to HNT, so that NR cross NT matrix is thus formed. So the transfer function vector, which is denoted by NT cross NR matrix of the channel, and it is given as this matrix. So where Hij, for any element Hij, it is the complex Gaussian random variable that models fading in between ith transmit antenna and jth receive antenna. For example, if you consider H23, it means I is equal to 2 and J is equal to 3, which means the H23 is the transfer function that corresponds to ith transmit antenna to jth receiver antenna. Right? So this is how we need to form the mathematical model of a channel that appears in a multiple antenna system, especially in a MIMO system. Thank you.